You know that feeling when you're staring at a super complex problem and you just wish you could see the simple answer hiding in plain sight? Well, in the world of digital logic, that's basically the daily grind. But what if I told you there's a tool that does exactly that? A way to turn the messy into the simple. Let's dive into this amazing visual shortcut. Okay, so take a look at this. This monster of an equation, it's called a Boolean expression. Think of it as a set of rules, like a line of code for a computer circuit. It's literally the language our devices speak. But, just look at it. It can get really messy, right? And trying to build a circuit based on this exact set of rules, it would be way too complicated and super inefficient. So here's the big question. What if we could just get rid of all that complexity? What if we could take that messy line of text and turn it into a simple visual puzzle? One where the answer just kind of pops out at you. And that's where this incredible tool comes into play. We're talking about Karnaugh maps, or as everyone calls them, K-maps. They are the super elegant solution to that big logical mess we were just looking at. So what is a K-map, really? Well, to put it simply, it's a graphical way to simplify logic. It takes all the possible outcomes you'd find in a truth table and lays them out in a special grid. It basically turns abstract logic into a hands-on puzzle that we can solve just by looking at it. Pretty cool, right? Okay, so if you've seen a truth table before, you know it just lists everything out in numerical order: 0, 0, 0, 1, 1, 0, 1, 1. Simple enough. A K-map, though, takes that exact same information but shuffles it into this really special grid. Now, the layout might look a little weird at first, but trust me, that specific arrangement is the secret to the whole thing. And here it is, the secret weapon. Look closely at the order. It goes 0, 0, 0, 1, and then it jumps to 11 before it goes to 10. That's not a mistake. This is called Grey Code. And here's why it's so important. Between any two neighbors in that sequence, only one single digit ever changes. Just one. That is the key to how this whole puzzle works. So burn that into your brain. All right, enough theory. Let's actually put this into practice. We're going to take a function, plot it onto our K-map grid, and get all our puzzle pieces in place. Okay, here's our example function. Now, don't let the notation freak you out. It's just a shorthand way of listing which combinations of inputs are going to make our circuit turn on. So you can think of these numbers 1, 3, 5, 6, and 7 as the winning combinations, the ones where the output is a 1. And this is what it looks like on the map. It's super simple, really. We just pop a 1 into every box that matches one of our winning numbers. So cell 1 gets a 1, cell 3 gets a 1, cell 5, and so on. Every other box, it gets a 0. And just like that, our puzzle is all set up. Okay, now for the really fun part, actually solving this thing. To do that, we need to know the rules of the game. So let's check them out. The rules are actually pretty straightforward. First, you can only group ones that are next to each other. Second, your group sizes have to be a power of 2, so you can have groups of 1, 2, 4, 8, and so on. Third, your goal is to make the biggest groups you possibly can. And finally, you have to cover all the ones using the fewest number of groups. That's it. So, let's start small. When we group two ones that are next to each other, that's called a pair. Now remember that gray code we talked about? This is where it pays off. Because of that special ordering, those two neighbors will only differ by one single input variable. One will have a 0, the other a 1. By grouping them together, we're basically saying, hey, that variable doesn't matter. And poof, just like that, one variable gets eliminated from our equation. Now, what if we can group 4 ones together? That's called a quad, and it's even more powerful. Inside a group of 4, you'll find that 2 variables change from 0 to 1, which means, yep, you guessed it, neither of them matter. This one move eliminates 2 variables all at once. You see the pattern here? The bigger the group, the simpler the logic gets. And here is maybe the coolest, most clever part of the whole thing. The map wraps around. You have to imagine it like it's a piece of paper you can roll up. So the top edge touches the bottom edge and the left edge touches the right. It's kind of like a donut shape. This wraparound trick is awesome because it lets us find hidden groups that connect across the edges, groups we might totally miss otherwise. Okay, so we've got our ones plotted, we know the rules, we are ready to find the simple answer that's been hiding in this map the whole time.
So let's take that big, ugly expression from the very beginning. If we plot that one on a K-map and follow our rules, we find we can circle a big group of 4 ones, a quad. Now, if we look at what stays the same inside that entire group, we'll see that the variable a changes, so it's gone. The variable c also changes, so it gets eliminated too. The only thing that stays constant for that entire group is that b is always a 1. And so, that whole complicated mess of logic from the beginning simplifies down to just B. Seriously, from all that to a single letter.
And to put a number on that, just how big of a deal is this? Well, the original expression would have needed a whole bunch of logic gates. Those are the tiny electronic switches that do the thinking. The simplified version, it needs just a single wire for B. That's a reduction of over 75% in the parts you'd need to do the exact same job. That is a massive leap in efficiency. So, okay, why do we even bother with all this? I mean, why is making things simple so important? Well, believe me, this isn't just some clever classroom trick. It has absolutely huge real-world consequences. The payoff is just gigantic. Simpler logic means faster circuits because the electricity has less junk to travel through. It means our gadgets are cheaper to make, they use less power, which is a huge deal for everything from the phone in your pocket to giant data centers. And for the engineers building this stuff, simpler circuits are a lifesaver. They're way, way easier to design, test, and fix when something goes wrong. You know, the Karnaugh Map is such a great example of how sometimes the best solution to a really complex problem isn't about crunching more numbers or using more brute force. It's about taking a step back and looking at it from a completely different angle, a visual one. And it really makes you wonder, doesn't it? How many other complicated problems out there are just waiting for someone to discover the right kind of map to solve them?